by the China Scholarship Council, and I'm supervised by Dr. Fudos, Professor Benmon, and Professor Li Hang. Today, I will present my work in the field of non-rigid three-dimension shape analysis. First, I want to talk about the motivation of this work. Shapes in three dimensions are often given as bounding surfaces, while in computer, it is often saved as a mesh or point set. Such a way of representation is suitable for rendering or visualization. However, it is not convenient for shape analysis, such as structure detection, surface matching, or shape classification. Therefore, it is required to derive a new way of representation for shape analysis, that is, shape signatures. In addition, deformed shapes are everywhere. It is also very challenging to represent and analysis. Early research on this field mainly focuses on rigid shape analysis, while in this work we focus on non-rigid transformations. Therefore, the goal of our work is to design a local shape descriptor that is invariant to non-rigid transformations. Our method is based on the recent development of diffusion geometry. The heat diffusion process over a Riemannian manifold can be described by the heat kernel. It measures the amount of heat that transferred from one point to another at a particular time. It characterizes the shape up to asymmetry. Particularly, it can characterize the local surface in multi-scale. Since heat diffuses progressively to a larger neighborhood, the time parameter provides a natural notion of scale to describe the local surface. To be specific, the heat kernel with a small t reflects the local property of the local surface, while larger t reflects the global structure of a larger neighborhood. Here is the overview of the extraction of our heat propagation contours. First, we set a list of time parameters to describe the local surface around the feature point in multi-scale. For each time t, we extract an external contour to describe the extent that heat has diffused around the feature point, and several internal contours to extract more information from the local surface. For each contour, we extract three statistics. The heat value of the contour, the average and variance of the geodesic distances from the feature point to the contours. Finally, we can create all these statistics together to form the final feature descriptors. We made two experiments to test the effectiveness of our descriptor. The first one is tested on the Tosca dataset. We can see that our descriptor achieved better performance, especially at the first few matches. Also, with the number of contours increases, our descriptor can achieve even better performance. The second experiment was carried on the Shrek 14 human dataset. Combined with the back-forward framework, we can see that our method can also achieve satisfactory performance. To conclude, in this paper, we propose a novel adaptive neighborhood scale selection method, and we propose a novel local shape descriptor that is invariant to non-rigid shape transformations. But in the future, we will investigate the influence of noise mesh resolution to our local shape descriptor, and also we are trying to propose a key-point detector to combine with our descriptor. That's all. Thank you.